Hello, OChem students. This video is going to be a continuation of the reduction. So I did hydrogenation last time. So we are going to jump over and do DMR and hydrides. All right. So remember, we're just talking about generic reduction, and there was the three ways: hydrogenation, DMR, and the hydride. So here's the dissolving metal. This one uses a radical. And we will talk about radicals in the future, but I'll give you a generic mechanism, but you'll really understand it when we get to the radical chapter. All right, so basically 2 protons and 2 electrons is what is needed. And the key is we're going to use a metal as a source of those electrons. So either lithium metal or sodium metal. So not ions. These are the lithium or the sodium metal. We also use liquid ammonia, and then of course we have to protonate with something. So that could be the ammonia, or in the end you could finish that out with ethanol. Now, if you'll notice, I put a nice little -78 degrees. We will learn later on that it's hard to control radical reactions, and so temperature is one really good way to do that. And so a -78, I'm just saying, hey, do this very cold. Well, the general mechanism for it is, let's take an alkyne, and we're going to draw, and I'll just use sodium this time. And that's not a plus sign. That's sodium's electron. Okay, that's its valence electron. Well, the radical mechanism would be to take away that electron from sodium. And if you break the pi bond, one electron has to go in each place. So now I'm left with a vinylic, both anion and radical. Or I could have done it vice versa. I could have put the ion over here and the radical over there. All right, well, what good is that? Well, I also have some ammonia around as a proton donor. And so the ion is going to rip the hydrogen off, and it's going to create that. So I still have a radical, but I have now put a hydrogen on in that location. Now, the key here is, should I leave the radical in that location? Is there any stereochemistry involved? It does form the trans products more preferentially. So this species right here, I'm going to draw it with some stereochemistry. There's one possibility. And there's one possibility. So in this case, stability-wise, when I get to change colors here, when I get to this step, the most stable form of it is actually in the trans configuration. And so this is the one that goes on and creates the product. So I'm going to change that electron to right there to indicate that. Well, then we start the entire process over and we do it twice. So we have another, did I use lithium or sodium? We have another sodium. So remember that one would have been cis. And we do the exact same thing. Now I know that's getting really ugly. I'll go to the whiteboard in just a minute and show you. All right, well, when are we going to have to worry about dissolving metal reactions? There's really only two ways. We're going to deal with alkynes. Well, why would we do this? Because I gave you a few ways to make cis alkenes, but this is your only way to make trans alkenes. Because remember, hydrogenation is a syn addition, and there's no way to get a trans. So if you want a trans alkene from an alkyne, you have to use dissolving metal reductions. And then benzene does something really fun. Benzene, in the presence of DMR, will actually form a cyclohexene. It's a diene. So it's 1, 2, 3, 4. So it's 1, 4 cyclohexadiene. Okay, very unique. Now there is a benzene chapter, and we'll talk about that again, but it does use dissolving metal reductions. All right, I know I gave these two as a example for you, but I'm going to go to the whiteboard and do both of those. All right, so get out of this one, go to the whiteboard. All right, so let's do that first one. So we have our nice alkyne, and I'm going to do the whole mechanism so that you can see the whole thing. So we have our sodium ion. So we're going to start that radical ball rolling, and we're going to create, and I'll actually follow the picture that I drew this time. So I will put the radical right there and my negative right there. But right here, okay, this is where we have some stereochemistry. So I can either draw this as that or as that. And the trans is more stable. Okay, so I just redrew it. And I'm going to react that with the ammonia. Whoops, there's a double bond right there. Okay, so there is the first step. There's the first step. I still have a radical. I also have some more sodium. Freem, freem. And I have another ammonia. And lo and behold, I end up with a transalkene and another NH2 minus. So that's the mechanism of the DMR for alkynes. And it's the only way we have for making a transalkene. All right, so there's for the alkynes. I don't have a whole mechanism for you for the benzene, but I do want to point out one important thing. And you already knew this, but when you do dissolving metal reduction, if you have a substituted benzene, I could have ended up with that, or I could have ended up with that one. Zaitsev says the most substituted alkene wins, so this one is the major product. And you technically don't even have to draw that one because this is the only one that truly would be formed. So if you have a substituted benzene, make sure you look out for the product and make the most stable product. All right, there's DMR. And if you'll notice, I write the word DMR above the reaction arrow. Feel free to do that, but make sure you do recognize the conditions. Okay, make sure you do recognize the conditions when they're given to you. All right, so our last reduction is our hydride reduction. Okay, now this one is probably the most useful, or at least the one that we're going to use the most often for the rest of the semester, is because we're basically using hydrogen as a nucleophile. Wait a second. H minus should not be considered a nucleophile. H minus should be considered a strong base, but we're going to attach it to something. Okay, so the hydride is attached to a metal, boron, lithium, aluminum, and the key is it is not a strong base anymore. So the hydrogen is not a strong base. It is just a good nucleophile. So these reagents, when you see them, you should see the hydrogen, not the entire reagent. All right, so the first one is lithium aluminum hydride. And if you'll notice, there's going to be 4 of them on here. And yes, it can use each of those hydrogens. All right, so there's what lithium aluminum hydride looks like. Sodium borohydride, not quite as strong. but it looks the same. Okay, so very strong, and this one is not quite as strong. But then, well, what if I don't want it? Okay, that strong. This one is very strong. This one is more mild, but not very selective. Okay, I guess that kind of is contradiction. It is mild, so it's selective because some of them are too strong for it to work on. But I really need, okay, now this is a jolly term, a poisoned hydride. Okay, so just like we did a poison catalyst, I need one that isn't going to continue on. And those two is this really long thing and one called dibal. Okay, so this one is lithium tri-tert-butoxide. Okay, so this is what this one looks like. So aluminum with a T-butyl group, a T-butyl group, a T-butyl group. Okay, so there's three of them. So there's the tri, then it's got a hydrogen on it, and that is a negative charge. And so there's the lithium. Okay, it doesn't have a fun name that's, used throughout, but it's I'm going to run out of room. This is a tri-tert butoxy aluminum hydride. So I tend to say TBA. Okay, it's really, is it a thing? No, it's just my shortcut, or TBA if you like. So that is this one right here, TBA or TBA, whichever one. All right, now dibal, that is a name that is commonly used, that we don't even draw the molecule out. We just say dibal. And so that one is an aluminum with two, wow, that was ugly, two isobutyl groups with a hydrogen. Okay, so diisobutyl aluminum hydride. DIBA. Okay, so that's where that terminology comes from. Those are more selective, and I'll show you that in just a second. Okay, but we know these hydrides act as good nucleophiles instead of strong bases, so they like to do SN2 reactions. And then you have to finish, the reactions off with a proton source, water, an alcohol, ammonium chloride, something. And basically, we're going to be reducing some polar bonds. So we're going to look at the alkyl halides, or anything with a really good leaving group. For this one, lithium aluminum hydride or sodium borohydride works just fine. And I am going to go over to the whiteboard. All right. So we are talking about alkyl halide reduction. Just going to take a generic one. Okay, that's a primary alkyl halide. And I am going to use lithium aluminum hydride or sodium borohydride. The key here is when you see that, you really should be visualizing this, okay? And technically there's four of them, but that's what you should see. Oh, look, that's just a nucleophile. There's a leaving group. Nucleophiles can do two things. They can rip off hydrogens or they can attack carbons. And remember, the reason that these are attached to a poisoned area is so that they act as a nucleophile. So we are going to create ta-da! And we can do it 4 times because the aluminum hydride and the borohydride actually have 4 of them. So if you want to get rid of that, if you want to use it up, throw something at it, throw some water at it, throw something so that you use up all of the hydride. And if you have a piece on your molecule, it will also protonate it. So I'm going to take a little side note right here. and I want to talk about protonation. Okay, protonation is fairly easy in organic chemistry, and so we tend to just, oh yeah, it'll get protonated, but I wanted you to see the species. So water can be a proton donor. Okay, alcohols can be proton donors. We could also use ammonium chloride. Okay, that's a nice one. Very, very good to give a proton. Or we could use an acid. I do want to warn you about the acids though. Number one, what if this is a halogen? Okay, so what if it's binary with a halogen? Well, then you create a competing nucleophile. So the rule of thumb is don't use a binary halogen. Okay, so HCl, HBr, HI, don't use those because it would rip off the hydrogen, but then you would have a competing nucleophile. All right, well, what acids are fair game? Well, pretty much the others, but, but, if you make it too strong, it's going to do other reactions. So it has to be a fairly weak or dilute. Okay, strong acid. I mean, you could throw vinegar in there, I guess, but if you just want protonation, we generally don't say which acid it's coming from with the assumption that you're not using one of those and you're not using concentrated sulfuric or concentrated nitric, just enough to give you a proton, but not do anything else. So that's what I mean when I talk about these protonation steps. All right, so that was your alkyl halide. And you're probably saying, why in the world would I use a hydride to get rid of um, that chlorine? Seems a very expensive way to do it, and you would be correct. Okay. All right. And the alkyl halide group, remember that's from the SN1, SN2. Methyls for SN2s are better than primaries, which are better than secondaries, which are better than tertiaries. Okay, so we can use lithium aluminum hydride and sodium borohydride. Well, another functional group that we need to consider is an epoxide. And I know, looks very silly. Remember, this is a three-membered ring, but it has an oxygen, so it has a built-in leaving group. And if it has a built-in leaving group, the hydride is going to love to attack. And this is symmetrical, so it won't matter which side. I pop that open, and I'm left with that. Now, in this case, I need to protonate, not only to get rid of my lithium aluminum hydride or my sodium borohydride, but I also need to protonate that. So you may use lithium aluminum or sodium borohydride. Either one of those will work. I'm going to go over to the whiteboard because what happens if it's not symmetrical? And the funny thing is, later in this very chapter, we're going to talk about how to create the epoxides. You probably don't even remember us talking about it in the past, but we would oxidize an alkene to get that, but we'll just assume it's already formed. There, I know it looks ugly. Hey, there's an epoxide and it is not symmetrical. So with my lithium aluminum hydride or my sodium borohydride, remember that's what you're supposed to be really seeing. Should I attack here or should I attack here? Now, there is a rule when we are doing epoxides, and it's based on sterics, of course, or electronics. Now, this one doesn't have any, positives or negatives. So hydrogen is tiny, but this one has no sterics. where this one has a little bit more steric hindrance. So this one is probably, for hydrogen, is probably the first case. But it's really small itself, so you probably will get both. All right, so I'm doing color. We're going to do this one first. All right, so we're going to go in and, wow, it's really getting ugly now. And then, of course, we're going to protonate. That will get rid of the extra hydride and protonate out. Wow, that looks so ugly. There, I'll put it so it looks a little bit prettier. 1, 2, 3, 1, 2, 3, and there's your hydrogen. And there's your hydrogen. So in this case, what do you get from an epoxide and a hydride? You get an alcohol. Okay, you get an alcohol. Well, what would happen if it went to the other location? You would end up with 1, 2, 3. You would also end up with an alcohol. All right, now this one is a primary alcohol, where this one is a secondary alcohol. So again, there is a difference, so it will matter which location. And if there's nothing special going on with this epoxide, okay, if there's nothing special, steric should rule, and it should be this location, should be the major product. And we do have a whole section on epoxides later on, but that is the generic gist of them. All right, so we have seen our alkyl halides, the epoxides. Well, what about aldehydes and ketones? Guess what? Built-in leaving group. And so this could be a hydrogen or a carbon. Okay, built-in leaving group, because carbon-oxygen bonds are polar, and it's also a pi bond, so it's weak and polar, double whammy. So we take our hydride and whoop, and then of course protonate. And this is the hydrogen from the aldehyde. Okay, but I am going to go to the whiteboard and do another example that's bigger and prettier. All right, that was an example of an aldehyde. Let's do an example of a ketone. All right, so we've got our wonderful little ketone right here. So lithium aluminum hydride or sodium borohydride. Okay, sodium borohydride isn't very strong, so it's used really nicely for aldehydes and ketones. So I'm going to put sodium borohydride right here. So the first step would be reacting with sodium borohydride, and the second step would be to protonate it. And remember, that's okay. We can stack different reactions above and below the reaction arrow. So you do the first step, this one, and what you should really see when you look at sodium borohydride is that, oh, I need to kick out a leaving group. Okay, why did I put the squiggle? Remember, this is flat. It's sp2 hybridized, so you can attack from the top or the bottom. So I can't control which side it goes, and the squiggle is showing you that there is both. All right, so the hydrogen looks ugly coming from right there, but there's the hydrogen from the hydride. Then, when we're finished, we need a proton source, okay, one of those proton sources. It would get rid of the extra sodium borohydride, but it would also protonate that. And this one would give you a secondary alcohol. All right, so sodium borohydride is a great reagent, but you could use lithium aluminum hydride as well. All right, two more. What about carboxylic acids? Okay, now carboxylic acids are very special because of the word acid. Nucleophiles can do two things. They may rip off hydrogens or they can attack carbons. We'll get what guess what acids are? Acids are, protons, hydrogens that want to come off. And so usually the first thing that happens with a carboxylic acid is some kind of acid-base action. And that is true. Okay, that will happen. So if you want it to continue on and a hydrogen, I'm not going to do the whole mechanism. If you want it to continue on and the hydrogen actually go and make an alcohol, you can't use sodium borohydride. You're going to have to use one that's really strong. And so the only one that will work is lithium aluminum hydride. And that will take you down to a primary alcohol. Primary. Last but not least, okay, carboxylic acid derivatives. Now, the carboxylic acid derivatives are pretty much everything else. Pretty much everything else. The only one that seems a little weird is a nitrile. Like, I don't see the connection. How's that a derivative? It's because you can go back and forth in reactions and make carboxylic acids from them, or they can be created from carboxylic acids. That's why they're called derivatives. All right, so all of those are much, much sturdier than like the ketone and the aldehyde. So you cannot use sodium borohydride. It takes a strong reagent, so only lithium aluminum hydride works. Well, what if you don't want to go all the way back down to alcohols? Right? That's when we start using those two special reagents. And I didn't leave myself enough room here, so we will jump back here. All right, and I will just do an ester first. All right, so there we have our wonderful ester. 1 lithium aluminum hydride, and 2, we'll need to protonate it. And again, when you see a hydride, that's really what you should be visualizing. It's going to come. All right, now we can nitpick this mechanism, but just generically, that is what we have. Oh, well, what happens if I protonate this? This is a special molecule. Hey, I have an ether and an alcohol on the same carbon. That's called a hemiacetal. We will also talk about those a lot in the future. Okay, the key is that is not the stopping place. That is not the stopping place. So I'm going to give you the Jolly mechanism. Keep in mind it's a shortened version just for convenience. So, right, we were right here. Okay. So the shortened version is, oh, look, I will attack again and kick that off. No, it's not a good leaving group. I'm just trying to simplify it. Oops, that's supposed to be a squiggle. All right, and so this is the hydrogen from the hydride, and then we protonate, and we would create, where are we? Sorry, I lost my place in we're ending up with a carboxylic acid. Oh, because I skipped that step. We're going to go from the carboxylic acid, but we're eventually going to end up with the alcohol. Sorry, I skipped through that step. All right, but we're going to end up with an alcohol because we know that actually then goes down to an alcohol using lithium aluminum hydride. Now that mechanism I know is ugly, ugly, ugly. So here's what you visualize. And it's not even the complete mechanism, just a visual. All right, if you see a hydride with an ester, it has to be a strong one. Lithium aluminum hydride is strong. It is going to convert that down to the alcohol, down to the alcohol. And this carbon is this carbon, and this carbon is that carbon, and that oxygen is that oxygen. There's the hydrogen from the hydride, and then this one was protonated. All right, so the key is it's going to go all the way down to an alcohol. Now, before I do the other reagents, I want to go back up here and now make sense of this. Okay, so I have separated them into their strengths. So lithium aluminum hydride is very strong. So it will take aldehydes to primary alcohols. It will take ketones to secondary alcohols. It will take carboxylic acids to primary alcohols. And so remember, this carbon right here is that carbon right there. It'll take esters to primary alcohols. It will take acid halides to primary alcohols. Now, amides, though, if you'll notice, have nitrogen, so it's not an alcohol. It takes it to an amine. And nitriles will go to amines, okay? Except for the ketones, those are all primary alcohols. And I will show you the amine in just a minute. But that is the strong reagent. Down here, I'm showing you the selective or the weaker reagent, and I only show it for ketones and aldehydes, which go to a primary alcohol and a secondary alcohol. But it's down here because I'm calling it weaker or selective. All right, what is hydrogenation? Hydrogenation is considered strong, okay? All right, your poisoned ones are down here because they're selective, and DMR is selective, so that's why those are there. So I need to show you this still, and these two, and those two. But I wanted you to visualize how it shows up on your reference sheet. All right, let's do, well, you've seen kind of the mechanism for a carbonyl, so let's do a nitrile. All right, that's what you're supposed to see when you see a hydride. Oh, look, built-in leaving group. So there's the first hydrogen. There's the first hydrogen. All right, and we have a negative. Now again, this is the jolly version. It's not the whole technical. We're going to react it with another one. Wait a second, that nitrogen isn't going to take on a negative 2. No, it's not. This is just a visual, a simple one. Oh, look, we need to protonate that. And there's a negative 2, so we'll have to protonate it twice. Oh, no, 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 that's not good. And we would be left with RC. Okay, those two hydrogens are now there. And NH2. Again, that's a very bad mechanism. There's details that I'm not showing you. This was the simplest version to get you to see it. Nature doesn't like -2s though. Okay, so we're going all the way from a nitrile down to an amine, and it's very similar variation for the amide. All right, last but not least, let's go back to our two specials. All right, remember I call this one TBA, and this one is dibal. Well, what is the purpose of those? Remember, they're selective. Again, a jolly term, they're poisoned. So these three reactants stop at aldehydes. Okay, they don't go all the way down to an alcohol. So they're again poisoned. So that instead of going all the way back down to an alcohol like lithium aluminum hydride, they actually stop at the aldehyde stage. All right, and that takes care of our reducing agents. So we have hydrogenation, we have DMR, and then we have the hydrides. And yes, hydrides are just nucleophiles. That was all SN2 reactions for the most part. And then I have some problems for you. And the way I designed this is react this one with this one. Okay, first react it with lithium aluminum hydride, and then react it with sodium borohydride, and then one of these two. So you're not doing them all together. You're supposed to have, three different reactions. So for instance, 1, 2, so this, okay, is the first one. Now these two would be the same in this case. So 1 or 2, because alkyl halides can react with lithium aluminum hydride and sodium borohydride in the same way. Again, you don't have to draw the mechanism, but sometimes it's nice to go back and see it. And there you go. So there's your first step. And then, of course, your second step would be protonation. All right. Well, what about dibal or the other one, TBA? That is selective, and alkyl halides are not one of its selective reactants. So this case, it wouldn't react. There would be no reaction. And so I give you pretty much one example of all the functional groups that would be working right there. All right, and that brings us to the end of reduction and our reducing agents. Until next time, Jolly out.